Hi everyone. In this video we are going to look at a result called Stokes Theorem, which is a higher dimensional version of the Green's theorem. So recall Green's theorem, there was a closed loop C involved and a region. So that's similar is going to happen here. We have a region C with a positive orientation, which again means that stuff is the inner stuff is to the right, to the left, sorry. And we have a surface that it encloses, this surface which we are denoting by S. And there are a bunch of normal vectors coming out of the surface. S being an oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary curve C with a positive orientation counterclockwise or region to the left. Let F be a vector field whose components have continuous partial derivatives on the open region in R3 that contains S. So there's some vector field that's going through it. And the result says that the line integral, f dr, is the same as the surface integral of the curl of f ds. Now this is also kind of similar to fundamental theorem of calculus because let's just count. Remember what curl is, right? So curl is del cross f. So curl is del cross f. And what is del? Del is a differential operator. Which means on the right hand side you have a double integral, a surface integral, and then a derivative, and on the left hand side you have a single integral. And again the integrals in that sense sort of cancels out, right? Remember in the Green's theorem it was del q over del x minus del p over del y, which is sort of the two-dimensional version of curl. Because when you take curl, it's a cross product. When you take cross product, you have a determinant thing happening. So if you look at the determinant objects are some stuff minus some stuff, right? So it has a structure quite similar to the Green's theorem. Where would we use Stokes theorem? Well, in either direction. If you are finding a line integral and it looks like it's hard to do, and maybe the current is something simple like constant or zero or something like that, then you want to move to a surface integral. Alternately, if you are working with a surface integral and you can find a function f such that the curl of that of the vector field is what is given to you, you can convert the surface integral into a line integral, and that might be easier to work with. So this is just a handy tool for when you're working with a surface integral or with a line integral. Like when you're finding fluxes and you can go back to a line integral and vice versa. Let's look at an example. Evaluate the line integral when the vector field is given by negative y squared x and z squared, and C is the curve of intersection of the plane y plus z equals 2 and the cylinder x squared plus y squared equals 1. So what is the region that we are working with here? We have a cylinder based on x and y axis, but it's getting chopped off at an angle by this plane given by y plus z equals 2. And then you have just a regular cylinder, which is x squared plus y squared equals 1. Okay, so we can find the line integral directly as well. But let's see, maybe the curl is something simpler, right? So recall finding the curl requires I, j, k, the partial operators in each x, y, and z direction, and their corresponding components. So what do we have? Partial z, that's 0, and that's 0. So there's nothing in the I cap direction. For j cap, again, partial of x is 0, partial 0. So nothing in here. For k cap, partial of x is, with respect to x, is 1, and this is partial of negative y squared with respect to y. So we have 1 minus 2y. Oh, but there's another subtraction in there, so it becomes a positive. Which means curl f is a pretty straightforward 1 plus 2y. So instead of doing the line integral, f dot dr, which we are trying to find, I will do the surface integral of the curl f ds, because it is just 1 plus 2y dA. And because we are on a cylinder, which has a circular shape, we can use polar coordinates. Radius is between 0 and 1, everything is confined in this cylinder, and 0 to 2 pi, and we have 1 plus 2 r sine theta, and the conversion factor, which is r dr d theta. After that, it's just a straightforward integration stuff. You have r plus 2r squared sine theta dr d theta. And once again, I'm going to ask you to complete this part. And to verify, it should come out to be pi. So this is an example where we went from line integral to surface integral because that was easier. In the second example, we'll do the other way around. So it says use Stokes theorem, to compute the integral, the surface integral, curl f ds, where f is xz, yz, xy, and s is the part of the sphere x squared plus y squared plus z squared equals 4, and lies inside the cylinder x squared plus y squared equals 1, and above the xy plane. Okay, so let's draw this this region that they are talking about. So we have a half a sphere, and then trapped in it is this cylinder. And the region we are talking about here is this here. And it has a counterclockwise orientation. Okay, so first of all, we need to find this boundary curve C, right? We need the equation of C. So this boundary curve C is the intersection of the sphere and the cylinder. What do we know about these things? We know x squared plus y squared is 1, and x squared plus y squared plus z squared is 4. So x squared plus y squared plus z squared is 4. X squared plus y squared is 1. You've learned in solving nonlinear equations is one of the methods is elimination. So I subtract to get z squared is 3, which gives me z is root 3 and negative root 3, which we will avoid because we're talking about things that are above the xy plane. So I have z equals root 3. So now I can parameterize this curve. It's a circle, right? But z is root 3. So which means we will use the most natural parameterization, which is cosine sine and then a root 3. And we'll find the derivative, which is negative sine t, cosine t, and 0. Once we have that, we can rewrite the given vector field in this parameterized form. So what do we have? Xz. So xz is root 3 cosine t. Then we have a yz, which is root 3 sine t. And we have an xy, which is cosine t sine t. So now what does the Stokes theorem say? So based on Stokes theorem, we have that this surface integral of the curl is going to be the same as a line integral. But what is line integral? in the vector form, line integral is f of rt dot product with r prime t. And we have these two here. When you take the dot product of them, the z part becomes 0. So all you have is negative root 3 cosine t sine t plus root 3 cosine t sine t dt, which is 0. So we did not have to find the surface integral. By using the Stokes law, we changed the surface integral into a line integral, which came out to be 0 anyways. And so that's one of the other applications for Stokes theorem. That's it for this video. We will have one more topic left. So one more video for that topic, which is called the divergence theorem, which is goes further up in one dimension. So has a relation between a double integral and a triple integral. That's it for this video. Thanks everyone.